Good morrow, fellow humans. My name is Sean and I am obsessed with infinity. So join me as I attempt to unpick the infinity of what is. In the last chapter, we unravelled the long tapestry of time, from the universe's cataclysmic birthing through to its eventual heat death a Google years later. But that wasn't the end of the story, as the following photon age then stretched into a future history that was so seemingly endless that it rendered the ages of both light and matter as next to non-existent. But as debilitating as these thoughts can be, there is still one more tiny little detail that we've thus far failed to consider, which is that time passes across an unfathomably broad spectrum of speeds, fluctuating wildly from one point in the universe to another. And so what this shall inevitably mean is that the weaving of time threaded between our own unique now and these far-off ends of the universe will end up being a far more complicated tapestry than what these first impressions may have led us to believe. Though here, or somewhere within this tangled vicinity, is where our descriptions finally arrive at their theoretical ends. But can time end? Did time start? It's a tricky question to answer, especially considering that we don't really know what time is. For when we cast our mind's eye towards these final stages of the universe, to a world where nothing persists but free-roaming photons, it becomes increasingly difficult for us to keep a rational hold on this familiar phenomenon to whom we have given the name time. In 1905, just 2 years after the Wright brothers had famously taken their inaugural flight, and a mere 3 years before the invention of plastic, a young physicist named Albert Einstein taught us that space and time can be thought of as differing characteristics of a single interwoven material, a fabric that warps and pulls against the influences of speed and gravity. A fabric that we know today as space-time. The upshot of this universal tug-of-war was that the faster any individual moved through space, or the closer they came to a strong source of gravity, the slower their movement through time. What we had learnt from this inspired 26-year-old was that time is unique to the beholder. Time in the International Space Station runs fast, at least faster than it does on the ground. Right now, assuming you're upright, the flow of time at your head is running faster than the flow of time at your feet. It's a real-world phenomenon, though one hardly perceivable from the resolutions of train schedules and wristwatches. However, nowadays, with the invention of satellites and quantum timekeeping, the effects of time dilation have the potential to cause major disruptions. Our global positioning system, the GPS, which we can access from our phones daily without giving it a second thought, is guided by 24 satellites, each in orbit of the Earth at altitudes of 20,200 kilometres. That's 12,550 miles. And they're travelling at speeds of up to 14,000 kilometres per hour, or 8,700 miles per hour. Due to the time dilation caused by the lessened effects of gravity, each satellite's internal clock gains 45 microseconds every day, while due to the warpage caused by its high speeds, 7 microseconds are then taken back, leaving the slightest 38 microseconds to be accounted for if we are to avoid the exponential drift of map coordinates that would allow our little blue beacon to drift off its course by 11 kilometers in only its first day. But it's not all clocks and synchronization, as time dilation could just as easily be used to witness the far distant future. All anyone needs is a spaceship capable of travelling at speeds close to the speed of light. This is because for every minute spent travelling at 95% the speed of light, 3.2 minutes pass on Earth, and if we encroach further upon the ultimate limit towards 99.999999999% the speed of light, every minute of our time would then be relative to almost 1 year and 4 months for all those who were left behind. So, leave home at lunchtime on Sunday and arrive back in time for dinner 480 years later. There is, however, a finite limit to this warpage, as at the actual speed of light, the dilation becomes so intense that it renders the passage through time impossible. And so if we return to our previously described universe of lost and lonely photons, this is the universe we should be imagining. One lost within a single moment of unmoving time. At least, that is, from the perspective of the photons. Because from the point of view of a photon, time is meaningless. Unlike the time we experience, time for a photon is contained within a single moment, frozen within a collapsed dimensionless space. Its entire history is over as soon as it's begun. What this means is that there are photons out there right now, as ancient as the oldest stars and prepared to sit by as the entirety of the universe's history unfolds, that, from its point of view, has not only just emerged, but is already at those universal ends. I know, it's not a thought that sits well, and I can assure you, dwelling on it offers little relief from the perplexity. But it is nonetheless relevant, because it provides us with the context needed to ask the more fundamental question: is there time without change? This unanswered question is one of our oldest on the topic of time, if not the oldest. Indeed, this is a conversation that countless philosophers, scientists, and even theologians have added to across the ages, though it is probably fair to say that none have been more influential than the following three gentlemen. Beginning, as we so often do, with Aristotle. Time is nothing more than the measurement of change as perceived by the soul. And so by the logic of an Aristotelian worldview, no change is equal to no time. But the modern thinker's more palpable take is more commonly taken from Newton. However, this is not because Newton was more intelligent or enlightened, nor even that he had access to a broader wealth of scientific knowledge. No, Newton's thinking resonates so strongly with our own because modern intuitions are inspired primarily by his thinking. For Newton, time is an unwavering force, one which, once set into motion by the hands of an almighty, flows ceaselessly into an ever-oncoming future. Tomorrow is a day away, a year 365 days, and nothing, not even the death of matter, could ever hope to hazard time's relentless ticking. a fact that should remain true regardless of where one is in the universe or what they're doing. And though it may seem like an obvious position to take, the idea that time simply is, it is actually quite a clever and intuitive interpretation that time always moves at the speed of time, whether or not change occurs. But though it's genius, it's also wrong. As Einstein was to show, everything, including time itself, is relative. Because for Einstein, there is no universal tick to time, since each and every particle is only ever moving in time relative to the other particles. But this idea has in some ways brought the intuitions of Aristotle and Newton together, because for Einstein, as it was with Aristotle, change is also crucial. The critical difference is that so is perspective. The flow of time, represented by any rate of change, is only made meaningful when it is considered relative to another reference frame's rate of change. For those on Earth, time feels like it runs at the speed of time. But that's precisely what happens for those on the International Space Station. Only when their relative times are compared can we witness their underlying variances. And as for Newton's part, Einstein shares with him the claim that time acts like a dimensional fabric. The only difference is that for Einstein, the fabric warps. But the more profound lesson to be learnt here is not that time warps or that it's entwined with change. The revolutionary mind bend that is so often taken for granted is that there is a clear disconnect between the time that we experience and the time measured by clocks. From our perspective, time always runs at a fairly steady, though somewhat wishy-washy rate. But according to these clocks, time can flow at intensely varied speeds from one point in space to another. So then, which is the real time? Clock time or experiential time? And if our experiential time must be questioned, what, if anything, can we presume to know about time at all? For everything we know about time is understood within the context of how we experience it. Though Einstein's relativity remains an incomplete theory of time, it nonetheless continues to play the most crucial role in our evolving understanding, resulting in what is perhaps an overabundance of interpretation as each new generation tries to highlight what and how much is actually being said by Einstein and his most widely acclaimed work. One interpretation, often credited to Einstein himself, but should probably be left to his mentor Hermann Minkowski, or if you want to split hairs, the pre-Socratic philosopher Parmenides, is the theory of time known as the block universe theory. The idea behind this model is that due to the interwoven nature of space and time, as space exists omnipresently, so too must time. Meaning that the past, present and future would therefore exist simultaneously. What this is asking us to envision is an objectively real past and future whose present is only a matter of perspective. In this universe, you would not only exist in the present moment, but would be stretched out like the worm inside an apple, with your birth at one end and your death at the other. If this is the case, then time doesn't just wind down alongside the deterioration of matter, for it's been an illusion from the very outset. And as strange as this might sound, it is currently the most widely spread description of time shared among physicists today. There are, of course, some issues with this way of thinking, but we'll get to these shortly. But apart from the timelessness said to be found in this winding down of matter, is another timelessness, found at the other end of this temporal tether in the supposed beginning of time. yet another vision of the universe considered devoid of change and hence beyond time. But this too is a regularly misinterpreted concept. Even in the block universe model, this idea of time having a start is far from readily agreed upon. In fact, the something from nothing explanation that often tags alongside our description of the Big Bang is hardly supported by any of today's major theories. Since the story of the Big Bang first hit the presses in the 1920s, there have been many hypotheses about the nature of before or even after the universe, from bouncing universes to colliding multi-dimensional brains. But the reason why many of us still circulate this idea that space and time started with a bang comes down to a simplified coupling of Einstein's relativity with Edwin Hubble and Vesto Slipher's 1929 discovery that the universe is expanding. By combining relativity with inflation, one could suggest that in order to describe the beginning of the universe, all we have to do is simply roll the clock backwards and watch as matter traces its path back down its current expansion trajectory and into its initial Big Bang singularity, where time and space reach a state of infinite compression and then, as if by magic, cease to exist. It is this exponential compression into infinity that does once again appear devoid of change. But here is where our interpretations often get ahead of us, as at the point of infinite compression, they say, space and time and all that is within ceases to be. But if it comes to an end, then this isn't really infinite. This is why infinite compression is rarely accepted as anything more than just a mathematical conception. Ultimately, the only honest thing we can currently say about this so-called singularity is that it is the point where our equations begin to fail. Because beyond the very finite scale of the Planck length discussed in earlier chapters, there isn't much that can be said with any certainty at all. Of course, this mathematical break may in actuality reflect some absolute physical limit. Still, before we jump to that conclusion, we must remind ourselves of the limitations of mathematics, especially when dealing with infinities. Now, you will probably be happy to hear that I don't intend to dive into any equations or any rigorous breakdowns of mathematical reasoning, as, for starters, that's definitely not within my wheelhouse, though nor is it the point as to why we're here. However, as our shared pause in the crazy does unfold, I do intend to return to the topic and philosophy of mathematics on several accounts, as it will become increasingly important for those willing to follow me on this journey that collectively we gain a better understanding of this often inaccessible language, especially when considering how mathematics has been accredited with an almost godlike status. Maybe this is nothing more than a trope common of ancient tongues whose usefulness survived the millennia, as standing at 3,000 years old, mathematics is considered among the oldest of languages still found in widespread use today. But maybe there's more to it than this. Though why it stands relevant to us now is that at either end of the universe's lifespan, we reach these mathematical infinities, either as the singularity of the Big Bang or as the unchanging emptiness of the universal heat death. Changeless states often said to harbour the start or end of time. And so it has become necessary that we now determine whether we need to distinguish between a fundamentally mathematical idea of infinity that sees it as a solution to an equation and the conceptual infinity that we might use to imagine a foreverness of reality. So that's what we're going to get into next week. We'll take a moment to look into these difficulties before getting back into what they say about our understanding of change and time. When it comes down to it, a digital system can only ever at best be considered a description of an analog continuum, such as infinity or, as many would argue, reality. Time, too, might also fall within this category, though this would again depend on what time actually is. But even if time is a continuum, what's the issue with describing it as a series of points? Take, for example, the simple equation 10 divided by 3. Of course, when we do this, we get the answer 3 with an infinite of recurring 3's following the decimal. Nothing particularly peculiar about that. But what happens when we reverse the equation? Instead, we end up with a 9 followed by an infinite of reoccurring 9's. So what happened? What was lost? The reason for this is that infinity is not a number, it's an idea, and a fairly abstract one at that. The use of infinity in both mathematics and cosmology can of course be extremely useful, especially when attempting to describe events like the Big Bang. But just because the vast majority of science is built upon mathematics doesn't mean that mathematics is itself a science. In fact, mathematics is much more often akin to an art than a science. For just as mathematics can convey meaningful insights into the truths of our world, so too can great poetry. And though both mathematics and poetry have an ability to describe their truths with a degree of subtlety and fine-tooth precision beyond the abilities of the other, both are similarly limited by their very nature of being digital languages. These are linguistic and numeric structures born of our own creativity. And it is due to this origin that each language's primary service shall always be to serve humanity's intuition rather than offering up any non-fallible truths about reality. At our day-to-day scale of macroscopic interactions, mathematics, like any language, works perfectly well. It describes the world we encounter. One apple plus another apple is clearly 2 apples. But in order for this system to continue to hold up, we must continue to contain our descriptions to the realms of subjectively finite structures. Yes, we may now have 2 apples, but where in reality does one apple end and the next one start? Now, that might sound like a silly question, but once we start pushing into the atomic structures of each apple, those borders start appearing far less determined. Think of how it is when driving through the mountains, as we climb up into the clouds. When we arrive at the top, what we once saw as a clearly defined edge of the cloud becomes revealed as nothing more than just a haze of poor weather, a borderless fog of mist. Apples, and even the atoms which make up their structure, are themselves no more defined than that weather. And so, in order to render the digital language of mathematics capable of describing what it finds within these fluid edges of our material world, we have allowed for a very human level of creativity to enter into its practice. in mathematics, if we wish, we can just say that something exists, like an apple, use it as a rule and just see what happens. If the rule causes contrary results, then we can either abandon the rule, or we can expand the rule to state that we must simply avoid the aspect that caused the contradiction. In other words, mathematics has evolved alongside humanity, receiving the malleability prone to all of humanity's tools. And so, it has been this malleable tool, limited by its digital nature and obscured by the perspectives of humanity, that we have long used when feeling out the shapes of the world around us. Similar to how a bat will use its echolocation to locate obstacles within its environment, we measure our universe by sending out our equivalent in the equations, which we then follow in patience, hoping that we might one day hit upon some new wall. Now, clearly it's not as simple as all that. And mathematics has definitely proven itself as an extremely useful tool in the navigation of our universe. But we have to acknowledge that, just as it is with the bat, our successes will only ever reveal truths that have fallen within the direction and scope of our tools. Ultimately, we can never know what aspects of reality that our method has lost in its translation. And the nature of infinity is a prime example of this. Mathematics, broadly speaking, defines two types of infinity: countable infinity and uncountable infinity. These were originally described by Aristotle in the 4th century BC, but it wasn't until mathematician Georg Cantor got involved in the 19th century that our current understanding of mathematical infinities really took shape. Cantor's genius went largely unrecognised in his time, with his ideas receiving widespread criticism. And it has long been thought that it was this professional rejection, along with the mind-bending nature of infinity, that led to his spiralling depression and intermittent institutionalizations. But what Cantor was the first to understand was how the mathematical infinities relate to one another, thus giving us the ability to calculate infinities as sets by giving them cool names like Aleph Null, or Omega, or even better, Big Omega. Using these sets, we could now do number-like calculations with infinities, like infinity plus infinity equals infinity, or infinity minus infinity. Well, actually, you break things if you do that, but you get the idea. Infinities acting like numbers. Mathematicians tend to enjoy grouping things together. In fact, that's the very basis for what we call number theory. In our system of numbers, we have what's referred to as the integers. These are simply the natural numbers from 1 to infinity and their negative counterparts, -1 to -infinity. Beyond the integers are the rationals, or more commonly known to us as the decimals or fractions. Now, these can be finitely bound fractions like 0.5, or they can be infinitely repeating patterns such as 0.333 recurring, or 0.123123123 recurring. But together, the integers and the rationals make up all the numbers that are found in the countable infinities. But it's the uncountable infinities where things get a little bit more interesting. Here enter the irrationals. In textbooks, irrational numbers are usually described quite plainly as a number that can't be expressed as a ratio of any two integers. But put more interestingly, irrationals are the infinities that lay between the infinities. These are numbers like pi, which, unlike the rationals, doesn't have its thread of decimals repeating off into some cyclical pattern, but rather a never-ending, infinite randomness. A randomness that is so freakish that it tends to break any equation it enters. In short, many of these numbers are considered transcendental, in that they literally transcend algebra. In 1888, whilst in correspondence with several philosophers, Georg Cantor proved that the vast majority of numbers that are out there are in fact transcendental. What this means is that the infinite set of transcendental numbers is bigger than the infinite set of both integers and rationals together. Now, there is every reason that this should sound odd to you, because after all, are there not infinite numbers in each category? And is infinity not infinite? How can one particular class of infinite numbers be considered a majority? Regardless of whether it was a 1 to 99% ratio, surely both are still an equal count of infinity. Here lies Cantor's brilliance. When we refer to the count of numbers within a set, we speak of their cardinality. In the case of the irrationals and transcendentals, their cardinality is actually larger than the cardinality of the whole numbers. In fact, there's such a big difference between the two sets that if we were to have an infinite vase filled with every single number that there could ever be, you would be next to guaranteed that your chosen number would be an irrational one. But where does this so-called cardinality come from? At a guess, we could suppose that the cardinality of just the odd numbers might be half of the whole numbers, since they occur only every second number. But this would be wrong, as both the odd and the whole numbers do in fact share the exact same cardinality. Thus they are considered the same sized infinity. The reason for this is that they can still be put in a one-to-one correspondence with one another. Meaning, I could pair the number 1 from the whole numbers with the number 1 from the odd numbers, and then the 2 with the 3 with the 5, the 4 with the 7, and so on into infinity. Every number, whether odd or natural, would always have a partner, no matter how long we continued the sequence. So when is this not the case? There is a little experiment that shows how irrationals are in fact different. That's quite easy, and it's only going to take us a moment, but it does clear up this whole bigger infinity debacle. So here it is. Imagine you were to create a spreadsheet with infinite columns and infinite rows, and then filled each row with a string of infinite numbers, including all the rationals and all the irrationals. Then, by our own rationality, we should have a spreadsheet that contains every real number, an infinite collection of infinitely long numbers. But then, if we take the number that's in cell A1, and regardless of what it is, just add to it the number 1, and then move diagonally down to B2, again adding 1, and then C3, and then continue this trend diagonally, infinitely down the page. What you will have done is created a number that didn't appear anywhere within the original set of infinite numbers. Even if you were to argue that this new number might be just hidden somewhere far, far down the list, it wouldn't be the case, because our new number will always differ by at least one digit wherever the diagonal intersection occurs. And so we have created a number that cannot be put into the same one-to-one correspondence as before. Thus, a larger infinity. And that's pretty much it. What Cantor proved was that there is an infinite array of these different-sized infinities, all stacked within each other, with the most ultimate being absolute infinity. For Cantor, this was an infinity so beyond comprehension that he equated it with God itself. Indeed, Cantor saw his entire insight as being ordained by the great Creator, claiming that the transfinites were real for the very reason that God has told me so. Though Cantor's work may have struggled to find its feet in its own time, it has since been referred to as the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. But I, for one, have a small gripe. Not with Cantor directly, but with the mathematicians that followed, and the metaphor that they often used to describe his work. The linguistic error that has been encouraged the world over comes as a result of our tendency to describe things in terms of hierarchy. When describing the relations between these infinite sets, we often state that one infinity is larger than another, as I too have done here. Granted, even in textbooks, the word larger is more commonly bookended with quotation marks, revealing that silent nod to the audience and an acknowledgement of that blatant contradiction of terms. Since no infinity can ever be considered larger than another, as both are infinite. But this doesn't require us to deny the genius of Cantor, as what remains true is the relationships held between the infinite sets. These relationships show us how certain infinities can lay within one another, or even stranger, how infinities can happily reside within a figure that is finite. But beyond this, all infinities are still infinite. And so, because the language of sets is a language of relationships, we need to be very cautious about what metaphors we're choosing to use. For me, using a metaphor of scale, i.e. larger or smaller, seems entirely counter to the ideals of infinity. Perhaps one better option might be to use the spatial metaphor from a different perspective, such as when we're closer to a particular infinite set, we raise the resolution and thus cardinality goes up. In this way, sets of equal cardinality would not be deemed the same size but the same distance from the observer, or next to one another. Likewise, those with lower cardinalities are not smaller but further away. We need a metaphor that describes a density relevant to a finite segment of the infinite set, not one that declares knowledge of size total. This may be trivial, and it's likely that there are better options than those that I'm offering here. But as we shall continue to find, the metaphors we choose to use when considering infinities, be they mathematical or universal, can totally change the way we think about them. So for philosophical reasons, they must be highlighted. The way we talk is inevitably the way we think. And considering we are already using the digital languages of numbers and words to attempt descriptions of analog continuums, we just need to remind ourselves how this can prove problematic if left unchecked. though if you think that mathematicians have a problematic take on the subject, physicists can be downright cavalier with their infinities, as we will get into in the next episode. We will get back to our discussion concerning the start and end of time and the infinities therewithin. For as Richard Feynman once put it, we have designed a method for sweeping them under the rug. In our day and age, it's practically considered common knowledge that in the universe's earliest moments, the wholeness of nature and the entirety of everything was contained within an infinitely compressed point. But what does that really mean? The problem with thinking about the universe as an expanding bubble hanging in nothingness is that it forces us to either declare or abandon the actuality of nothingness. Many concede to this notion of nothingness by referring to it as merely the absence of things, a dimensionless non-spatio-temporality untouched by the ever-expanding bang. However, they will often then go on to grant this particular brand of nothingness the attribute of a potentiality, as in a nothingness capable of becoming an isness. But this isn't nothingness. At best, this could only ever be considered emptiness. And so philosophically, it becomes impossible to adopt this concept as a genuine example of nothing, since if it were an ultimate example of nothing, it would not host potentiality and we wouldn't be here. Now, sadly, this shall not be a discussion about the existence or non-existence of nothing. That's just going to have to wait. Because what we are still attempting to shine a light on is how time relates to change. Here, we are unfolding a relevant issue that arises when we declare the existence of an ultimate boundary, or worse, confuse infinity with one. So often in physics, the word infinity is used haphazardly in place of some extremely large or uncountable number, such as in the phrase tending towards infinity, often used as a catch-all to describe an event that builds exponentially. In reality, however, everything tends toward infinity. 1 tending towards 2 is still tending towards infinity. But more importantly, 1 tending towards 2 is just as close to infinity as is an exponential increase that leaps from the tens to the trillions within only a handful of steps. This just goes to show how much we are in the habit of confusing non-digital concepts such as infinity with digital ones, like ultimate borders, like those thought to separate banging bubbles of space-time from the hard-edged fringes of nothingness. As that philosopher Parmenides once wrote, nothing comes from nothing. And so, faced with this perplexity, many have chosen to dismiss nothingness altogether. But what then is our floating finite bang set within? In many of today's cosmological theories, we are asked to envision a description of nature that persists beyond the universe, outside of space and time. Here we are asked to imagine a domain capable of housing a potential infinite of universes, each with their own unique set of physical laws, separated by what could only be described as an ethereal isness of non-physicality, what we might call budget nothing. But even if we accept the possibility of such a domain, what is the nature of the boundary that divides us from it? Now, it is possible that we could live in a universe whose nature is both finitely bound, but also without end. We will try to navigate such a universe in later chapters, but for now, all we need to know is that a universe of this nature would never find its end, because at one point, it would begin repeating itself. Though this might not be as counterintuitive as it first appears, akin to how a straight line on Earth, having never turned around or left its flat two-dimensional surface, will eventually return to its starting point. The universe could similarly be curved in higher dimensions, allowing straight lines in space to also come back upon themselves. In a cosmos of this nature, we would never find a boundary separating our three-dimensional space from the faux nothingness, but nevertheless, the issue remains. Even in this model, our universe is still considered finite, meaning it must be bordered in some way or another. Often these mathematically derived physical theories describe the tapering off of physical reality where space-time falls down infinite ravines that are shaped by the universal constants of nature. Upon the fringes of the uncertainty principle, the speed of light or black hole horizons, where we often, once again, confuse these infinities with ultimate boundaries. We, as macroscopic entities, may be held back by them, sure, but that's not the same as saying that reality stops. Now, there is a small thought experiment that we can take from the last chapter, which in a peculiar way is actually very relevant to this same idea. This is the deceptively simple mathematical conundrum where a 10 divided by 3 fails to return to 10 after being multiplied by 3, leaving us with the untidy 9, followed by an infinite recursion of 9s. Now, let me just reassert my own inadequacies in mathematics and reassure you all that this shall be brief, painless and simple, but in the end, philosophically intriguing. Because there is actually a mathematical proof that tells us how an infinite recursion of 9s should be considered equal to 1. The proof works as follows. X is equal to 0.999 recurring. Therefore, 10x is equal to 9.999 recurring. Now, if you simply start with 10x and then subtract 1x, you will have 9x remaining. What this is saying is 9.999 recurring minus 0.999 recurring is just 9. But if 9x is equal to 9, well, then x must be equal to 1. Thus, 0.999 recurring is equal to 1. So what's the point? The point is that this so-called proof is actually an excellent one to meditate on because it forces us to ask what really is the difference between an infinite recursion of 9s and 1. In one sense, the infinite rational fraction seems to fall short of 1 since the recurring 9s are never resolved. To say that they are 1 is to say that the 9s found some end. And yet, in another sense, they must also be infinitely close to 1 with absolutely nothing left to be added. The chasm between 0 and 1 must be infinitely full. And so, what we are forced to ask is, what's the difference between infinitely close and arrival? Or, as it's relevant to our current topic, what is the difference between the infinite ravine of uncertainties, light speeds and black holes, often confused as borders, and continuation? But of course, as many of you may have already reasoned, this divide between space and nothing only remains an issue so long as we presume that the universe is finite. If, in contrast, we assume that our four-dimensional universe is instead infinite, well, then we have no need for a nothingness that is, nor any ultimate borders. And this is actually the more common belief that space and time go on forever. But this brings us to the reverse issue with our bubble-like interpretation of the Big Bang, as we now have to account for how this tiny singularity could expand into infinity within a finite amount of time. Since if we were to rewind our universe at exponential speeds from where its current infinite girth might rest today, back in time towards its singularity, we would never reach any starting point. It would, of course, continue rewinding for an eternity. On occasion, I have heard the odd expert claim that if we had an infinite amount of time, the universe would then be infinite. But this, as a statement, is utterly meaningless. Because if the universe had a start, it could never reach this infinite state, neither in time nor dimension. Even an eternal universe would never achieve these infinite ends. Thus, we are at a crossroads. For if the universe is finite, then we are forced to deal with the paradoxical nature of a nothingness bordering space and time. If infinite, then a finite Big Bang singularity would also prove paradoxical. But what if we were to consider the infinite compression of the Big Bang, not only as containing everywhere and everywhen, but also being everywhere and everywhen? Instead of it being an infinitesimal bubble, imagine the Big Bang singularity itself as that which is already infinite. A singularity without bounds. Not as some beyond sub-quantum grain, but as a literal infinite place, just as everywhere and always as is the universe today. To use a clumsy metaphor, an infinitely large singularity. But though we are, once again, forced to use metaphors, this one, in particular, does now feel somewhat familiar, as it parallels the other thought experiment from the previous chapter, which was our attempt to remove the language of scale from our infinite mathematical sets. There, we considered the infinite numerical sets not as hosting the attributes of largeness or smallness, but more qualities that were relevant to the observer, such as closer or further away, denser or sparser, depending on which finite frame it was that we wished to consider. And so, it seems that we could play with a similar dimensional transition here, only this time in the context of the compressed infinite universe and the decompressed infinite space-time. Instead of thinking of the universe and the singularity as being bigger or smaller than one another, we can think of them as being compressed or relaxed versions of the same infinite wholeness. In its compressed state, the universe could potentially host a nature not too dissimilar to that of quantum foam or the inner depths of black holes, and therefore be safely considered dimensionless in the traditional Newtonian sense. Whilst at the other end of the spectrum, in its relaxed state, the universe unfolds into what we see today, unwinding the quantum randomness into the traversable dimensions of space and time. To imagine this, we only have to see that the universe doesn't grow in size. It expands within itself. The retreating galaxies we see aren't riding a wave of space-time away from us. Space is expanding from within itself. We see this when we look up at our night sky, an expansion revealed to us in the red-shifted light of ever-receding galaxies. So let us consider a Big Bang that didn't just happen everywhere at once within a finite singularity, but one that happened everywhere at once within an infinite singularity, one which, by this rationality, we must still be within today. Therefore, the image of the explosions racing through an empty void that you probably had in mind when thinking about the Big Bang would be entirely fictional. For this event didn't just happen within some void of nothingness, it happened everywhere, infinitely. Now we mustn't confuse this with the fact that the traditional description of an expansion rushing outwardly from the original Planck-sized universe is still technically accurate from a certain point of view. It's just that the so-called Planck-sized universe refers more to a state of compression rather than size. Size, as we tend to think of it, is just simply not relevant when imagining this compressed state, as size is itself an attribute of nature that only became relevant with the emergence of our three-dimensional space. Prior to the emergence of traversable space, size was not a valid variable. But from the moments just after its initial birthing, we can safely say things like, the universe was the size of a baseball, but only with respect to the part that we call the observable universe. These tiny universes that we so often hear about in science documentaries are not the universe in its entirety, but only a small version of the bit that we see today. And so, within a model of this nature, I'd like to think that there kind of was no Big Bang, only what I would call a big relaxing, where from within some unique perspective of reality, a new dimension did open, allowing for space and time to become appreciable, but importantly, nothing new was added to reality in these first moments. This was just the emergence of new relationships. And just to add one further level of complexity to this ponder, though this may have been an infinite opening, relaxing an infinite of spatiality and temporality into existence, we could still consider this universe dimensionally contained, not by any ultimate borders or spatially defined edges, but by a transition of relationships pulled taut by the infinite ravines that we recognize as the laws of nature and the universal constants. A loose bookending of space-time, shaped by quantum uncertainties, light speeds, and black holes. And so from broader perspectives, a universe, whether endless or limited, could be considered much more like the borderless atom or the haze of poor weather that sits upon the mountaintop, each unique and individual through one set of eyes, whilst equally entwined and at one with the wholeness of reality through another, offering us a picture of reality quite reminiscent of our mathematical sets, with infinities harbouring infinities. Of course, this is purely hypothetical. But then, so is every theory concerning the universe in these earlier states. But if nothing else, I do hope that this short series of thought experiments has given you a taste of what considerations are forced upon us when we acknowledge the infinities that lie hidden behind a label of boundary, since we can never almost be at infinity. Infinity either is or is not. So, what does any of this have to do with time and its relation to change? Well, as we might recall, these ends of time are the domains where change appears lost and time is declared null. Now, if you were to specify that this temporal cessation refers solely to time as we know it, well, then you might have a case, since then we were talking about something particular to our perspective. Or even this would require a knowledge of what time as we know it is. If we were to declare that time is nothing other than an aspect of change, flow, or flux, then all we have to ask is whether these qualities find themselves up against ultimate boundaries as they sink down into the infinite ravines described by physics. Do they meet? The the walls of nothingness? I think not. Reality doesn't begin or end with singularities. It just shifts gears through them. As Stephen Hawking famously remarked, asking what was before the Big Bang is like asking what is north of the North Pole. It's not that the answer is nothing, it's that the question is wrong and that we must continue our search for those better questions. And so in truth, we can't yet say what time was like before the Big Bang, nor what it will be like during the photon age following the heat death of the universe, since, if we're being brutally honest with ourselves, we don't even know what time is now, beyond our very human experience of it. Because just like the mirage of ultimate borders, time as a thing unto itself can only ever be appreciated in relative terms. So if we wish to consider the topic of time properly, then it now seems abundantly clear that we must first determine what perspective we are considering time from. From what perspective are we choosing to claim that time either does or does not exist? That it is equal or not equal to change? Albert Einstein described his own perspective of space-time as an expanding infinite universe, within which all points are relative, with no universal bed where space lies, nor any universal clock. A place where we move through space and time only in relation to other bodies. Thus, without the bodies, things, elements, or energy, there would be no way of appreciating any state of space, time, or even change. But that is only from this perspective, a perspective that assumes we could remove all energies from the universe, a perspective that presumes the possibility of another type of nothingness. From all imaginable frames, will we be forced to claim that change stops? Is time digital, like the mathematics we use to describe it, and hence capable of some final moment before being compressed into oblivion? Or is it analog, boundless and eternal? Does it roll from start to end like a bike down a hill? Or is it infinite, not only in its duration but also in its density and depth? At the ends of matter in the universe, it's clear that time does appear somewhat missing. But this is only because there is nothing relevant to our perspective that could show evidence of it. If we were to travel into the future and witness this universal heat death for ourselves, we would of course still experience time. But this is because we are the movement by which time is measured. We are the frame through which time would exist. From this perspective, we are time.